Hey, as we start our lesson on tangents, I got a little joke here for you. I think I'm punny. Okay, that was bad. All right, so remember what a tangent is. We have a circle, and we have lines associated with it. This, of course, is our secant line. In the middle here, from endpoint to endpoint, is a chord. But when we move this line around, if it comes outside of the circle, it doesn't really have any relationship. But if it comes and just barely skims, barely touches the circle, we call that a tangent line. And this point where it's hitting is our point of tangency, you might remember. So we're going to look at a bunch of theorems that have to do with how this tangent line relates to our circle. Theorem number one, any tangent line to a circle is what? Well, let's get a sketch. So get yourself a circle and draw in a tangent line. I'm not going to be using my tech here. I'll just draw a little line. Let's say right here. Okay, I missed. Pretend we got a hitting. There's our point of tangency. This first theorem has to do with the center of the circle and the radius. So sketch in a radius to that point of tangency. What do you think would be true about those two segments, the radius and the tangent line? Right here at the point of tangency. If you think they are perpendicular, making a nice 90-degree angle, you're exactly right. So any tangent line to a circle is perpendicular to the radius at the point of tangency. The converse of that is also true. Let's say in this case, you're looking at a circle, and you've got a line that is drawn perpendicular to a radius at its endpoint. So you kind of have to go backwards here. So you have a radius, and at its endpoint on the circle, you have a line drawn in perpendicular to that radius. So you know you have a right angle. This line right here. That would be a tangent line to the circle. So our theorem says that in a plane, any line that is perpendicular to a radius at its endpoint on the circle is also tangent to the circle. Now our third theorem, I'm going to let you kind of think about this. I think you can figure this out. What must be true of the two tangent segments in this diagram? The y is maybe the hardest part, but let me help you get started with the y. Let's draw the center in, and let's just sketch in the radius that goes out to this point of tangency, and the second radius that comes to this point of tangency. And to help you out, I'm also going to draw the line that connects this external point to the center. So, what's true of those red lines and why? Pause the video, give that some thought. All right, if you think those two red lines, those two tangent lines are congruent, you'd be absolutely right. Let's think about what we know. We know that this is a right angle from our first two theorems. And we also know that these are radii of our circle. And they form these two triangles. I'm trying to say that these two triangles are congruent. So far I have a side and an angle matching. And I'm going to look for one of my shortcuts. Let's use our shared side like we love. And what have we got matched up? We've got a side, another side, and an angle. And so side, side, angle. That was our does not work one, but notice the angle is a 90-degree angle, making this a hypotenuse. Let's change this to hypotenuse, and this a leg, and hypotenuse leg did work. So these are congruent triangles, and therefore we can tick mark these two red segments the same. So that's our third theorem. And I call this thing the Dunce Cap Theorem because it always reminds me of a kid wearing a dunce cap. If two segments are drawn to a circle from a point outside the circle, then they are going to be congruent to each other. So congruent right here. Okay, let's apply these in some examples. Our first example is showing how theorems 1 and 2 work. We're going to have to determine if segment KM is tangent to circle K. And I can see right here it's not. That is a typo. Let's change that. Let's call this segment LM. And we're going to determine if it is tangent to circle K. So the way we would know if this is tangent, this has to be hitting the radius at a right angle. That's our question. What's the angle right here? We know a Pythagorean theorem test can help us with that. Let's set up and see if 20 squared plus 21 squared equals this full length squared right here. Now that's only 9 on the outside. What's the whole thing? Well, I can take that same 20 as a radius and put it here as a second radius. So that makes the whole thing 29. And so 20 squared plus 21 squared has to equal 29 squared. And the real question is, does it? So the question mark is that equal sign. Let's calculate it out. 20 squared is 400. 21 squared is 441. And 29 squared, I don't have that one memorized. Let me punch that in my calculator. Okay, I'm getting 841. So does 400 plus 441 equal 841? It absolutely does. So yes, this is a right angle. I can put that in now, and I can definitely say that they are tangent. Yes is the answer. Same goes here. Let's start out with our question. Is this a right angle? Let's remember 11 is a radius. I'm going to put that here as well. And note that the whole side across this one is 15. So in our Pythagorean theorem, we're looking at 12 squared plus 11 squared. And seeing question here, does that equal 15 squared? So calculation time again, 144 plus 121. And 225 is our total for 15. So we've got 265, which definitely does not equal 225. So these are no, and it's not a tangent. Okay, now this example, we are going to be finding a missing segment. This is our question. And this is important. You'll see this in directions a lot of times. We are going to assume that segments that appear to be tangent are tangent. So they're not going to go through and tell us every time, but this segment here does look like it's a tangent line. It looks like it's hitting at just this one point right here. So we're going to assume that that's a tangent line. This is from the center down, this is a radius, so therefore I can put a right angle in this picture. That's our theorem. Note that the radius of that is the same 12 that we see over here. And so we're looking really at a Pythagorean theorem problem. Look at our hypotenuse. How long is this whole thing? Whole hypotenuse is 20, 8 plus 12. And so we just get to set this up like in any other Pythagorean theorem. It's going to be 12 squared plus our question mark squared, which we'll call x, set equal to 20 squared. Okay, let's calculate this out. 400 on the 20 squared. Subtract that 144 over and bring that total down to 256. And then taking square roots on both sides of that, the square root of 256. Oh, what am I thinking? It's not in a decimal. It is an exact. That's a perfect square. That's 16. I knew that. So x is 16. And we can put it in our picture. Okay, this one might be the toughest one on the whole video. So if you need to take a break, do it right now. Go to the bathroom, get a drink, pop some popcorn, whatever you need to do before we tackle this one. It looks innocent enough, doesn't it? But believe me, I've done this one. It's going to involve some algebra. Okay, so we have, again, we've got this tangent line. We have a radius drawn in. Let's put in the right angle. And we are going to calculate, again, the measure of the radius. So it looks like a Pythagorean theorem for me as well. The problem is this whole hypotenuse here is not known. The only thing we know is that this is a radius, but we don't know anything about it other than I can call it r. And so this whole thing is how long? 8 plus the r. That's all I know. It's going to make this a little bit more intense with the algebra, but it's still Pythagorean theorem. Let's set it up as 12 squared plus the radius squared. Set that equal to 8 plus r squared. Now here's where you got to be careful. You want to square the whole thing, so you need to put it in parentheses and square it all. How do you square this out? That's the big trick. So I'm going to do it a little side work. You have to remember that 8 plus r squared means that we're taking 8 plus r and multiplying it by itself. So I think you got to write it down twice. And then you're going to double distribute this. Sometimes people call this FOIL, if that rings a bell. I call it double distributing. We're going to take the 8 and times it by the stuff in this parentheses. So 8 times 8 is 64. And the same 8 times the r gives me 8r. And then I have to do the same with my second term, my r. So r times this 8 is 8r again. And then finally, r times r gives me r squared. And I'm going to say that's 64. This 8r and that 8r is 16r if we combine them, plus that r squared. So that's what I have to bring over here. This is just some side work. Show it, though. You got to know how to do it. Let's come back over here. So we've got 12 squared. We all know that's 144. And then bring down the plus r squared. Now this side is equal to, what did we get when we expanded it? We've got 64 plus 16r plus r squared. All right, let's deal with these r squareds first things first. Let's say I subtract r squared from both sides. And that's kind of nice because they just really drop out of the problem entirely on both sides. So I'm down to 144 equals 64 plus 16r. All right, now we're business. So taking away the 64, 16r is equal to I believe that's 80, and so then dividing by 16, we get r is 5. The radius of this circle is 5. Okay, what about using angles? Again, these are tangent lines, so they give us information that's not readily available. We can put a little right angle right here on that tangent radius intersection, and then we can find out what this missing angle is. Now this says we're going to use isosceles triangles. Can you find the isosceles triangle in this picture? Remember, these are radii. Radii are always congruent, so I'm going to tick mark them. This is my isosceles triangle right here. Okay, so let's solve that. 114 is the vertex angle. Let's take that away from 180. And we get 66. And then we need to remember our isosceles triangle theorem that these two base angles are going to be the same. So this 66 is going to get divided in half, each one of them being 33. So we got a 33-degree angle right here. We've got another one right here. You can just jot those down. Well, how does that help me find this angle? If I look at this in a different way, let's look at a different triangle. Highlighting this one, I'm going to look at this big right triangle, because that right triangle has 3 angles in it, and I know 2 of them. I know the 90, of course, and I know this one down here is 33. So my last one is just the remainder. So I've got 90 and 33. Looking at 123 there. If we take that from 180, we have our answer, which is going to be 57. Okay, here's a cool one. Why don't you pause the video right here too? See if you can remember this isosceles triangles, how it works in problems, and come back to me. All right, real quick walkthrough of this. Your isosceles triangle is right here. See how you did. There's the isosceles triangle. We don't know any of these angles in it. We have a 50. Let's see how we can use that to figure out this angle in the middle. So I've got a 50-degree angle here and a 90 right here at the point of tangency. Let's get our third angle of the right triangle. And again, let me highlight the right triangle so you see what I'm looking at. I'm looking at this triangle here. So out of our 3 angles, 90 and 50 are accounted for. That's 140. How much is left to make our 180 total? Last angle is going to be 40 degrees. So here we have a 40-degree angle. Right here in our isosceles, we have a matching 40-degree angle. So 40 and 40 taken away from 180. What's that last angle, that vertex angle there? It's going to be 100 degrees. Okay, give yourself a huge pat on the back if you got that, and go get yourself another snack too. Okay, this example we are looking at, again, this Dunce Cap Theorem. You can see why I think it, although some of you might on this example think more of like ice cream, because that's what that sort of looks like. Yeah, I think I might be hungry. Everything's about food with this. Okay, so this Dunce Cap Theorem, this is pretty straightforward. Nobody's going to call it Dunce Cap Theorem but me, probably. But I do know that from this diagram, these two tangents, and they are tangent, are going to be the same length because they come from the same point. So I can simply set these equal to each other and find my value of x. I know that 4x minus 1 will equal 3x plus 10. This is an old Algebra 1 problem. You guys have done these a million times. 3x is gone. So I'm down to x minus 1 equals 10. Add 1 to both sides, and x is 11. How easy is that? But my favorite kind of problems with this are these kind, where you get to find the perimeter of this circumscribed polygon. Notice this is on the outside, so the polygon is circumscribed, written around the outside. Can't spell it. And that means that the circle is inscribed. But we're going to find the perimeter of this. So all of these lines that we see, these are tangent lines. And of course, perimeter is added all up. So we only know one side of this polygon. Let's see how we can figure out the other sides. Let's take this one, for example. I know one piece of it, but my tangent lines are the same. And so this 8 that I see here, I can move down here. That's just a little dunce cap built off on that corner there. The same applies to all the rest of this. So all of this side can be found with the two pieces. Guess what this matches? This matches on the other side of that same dunce cap right here. So this is 5.5. And I have a match right here. I'll triple mark. Right over here is 7.4. And then my last little section, can you see it right there? This is tiny. These are going to match as well, but I don't know either one of them. Or do I actually? Look right here. I have this whole thing as 10, 8, and what's the other piece going to be? It's going to have to be 8 and 2 to make the 10. So 2 there matches 2 right there. And then I can just add up all the sides. So let's actually calculate them all. So this side right here would be 8 plus 5.5, or 13.5. Here on this side we have 5.5 and 7.4. So that's, I think, going to be 12.9. And right here, this whole side, this fourth side is 7. Whoa. No, it isn't. This whole side would be 9.4. Okay, perimeter, we're just going to add those up. You can do this. 10, 13.5, 12.9, and last 9.4 for a grand total of 45.8 units. And that's it. So that Dunce Cap theorem should make you feel smart. Give these a try.